Thank you everyone for joining the talk. I'm Indeed Hamid Islam from UNC Chapel Hill, and the title of my today's talk is Sound Adapter Multi-Source Domain Adaptation for Acoustic Classification through Domain Discovery. Voice-controlled personal assistants known as home app devices like Amazon Echo and Google Home are increasingly gaining popularity for interacting with smart home appliances, searching the web, daily activity monitoring, and so on. The ubiquity of acoustic sensing opens doors to many potential applications, including elderly monitoring, where the system is used for fall detection and daily activity monitoring. Acoustic sensing can also be used for sleep pattern recognition and patient monitoring, where the system is used to monitor if the patient is taking her medicine or drinking water or doing any prescribed exercises. A major challenge towards scalable machine learning based classifier for acoustic sensing is that the signals are influenced by recording devices such as microphone types. Therefore, the classifier models trained with data sampled with a particular type of sensor perform suboptimally when the model is presented with data recorded with a different sensor. For example, here the model is trained with one type of microphone's recorded data. During inference, when it receives data from the same microphone, it is able to correctly classify them. But when the model faces data from a different mic, it misclassifies it because of the biases of sensors on the classifier. And as there are a lot of different types of sensing systems nowadays, it is not possible to have uniform sensors across all the devices. Here we can see a typical scenario for a machine learning classifier for audio data. Generally, the developers collect data by themselves or use crowdsourced data collected by many recording devices. Then during inference, data comes to the classifier and it may be recorded by a different device of which the developer may or may not have any control. The recording devices used during training phase is considered as source domains, whereas the devices used during testing phase is defined as target domain. First, I'll talk about sensor heterogeneity. Here is the total pipeline of how the signal reaches the classifier. First, it goes through the sensor, such as microphone, and then the DSP chip performs signal enhancement operations. Then the operating system receives it and sends it to the application layer to the classifier. A small variation in this whole pipeline can cause a significant heterogeneity or variation in the sensor data. For example, different sensors have different response to different frequency. In the context of low-cost embedded devices, such hardware variabilities are likely to be even more prominent. Then the DSP chip on the embedded devices run a number of signal enhancement algorithms whose parameters are fixed by each manufacturer. For example, in the case of a microphone array, acoustic beamforming algorithms are employed to improve the SNR of the audio. However, implementation differences in such algorithms across manufacturers can lead to variability in the output audio data. Varying CPU loads can cause sampling rate instability, which further pollutes the signal. So, both the hardware and software components of this whole pipeline can introduce artifacts in the recorded signal. Here we see the effect of different sensors on audio signal. We record the same audio data with 5 types of microphones in the same environment at the same time. Only variable here is the microphones. We see from the time frequency representation that the signal exhibit difference in their feature for the 5 microphones. For these reasons, a significant classification accuracy loss of up to 20% is observed when the training and testing devices mismatch. That is when the source and the target domains are different. Now I'll talk about our proposed domain adaptation, which we name as sound adapter. The first step is unsupervised domain discovery. In general, the public datasets and the crowdsourced datasets do not have meta information about recording device or environment. Therefore, domain information or label is generally not available. So we need a method for extracting domain information without any domain label available for training. So we propose an unsupervised way to extract domain label. The most natural choice for unsupervised classification is clustering algorithm. But traditional clustering algorithm is not a feasible solution in our case. Here we see the sound of mixer and sync are being recorded by two different types of microphones. If we perform clustering on these 4 clips using k-means clustering, we see that the clusters are produced according to their event types. That is, the 2 clips from the sync is grouped together and the 2 clips from the mixer is grouped together. This is due to the fact that audio event traits are dominant in the audio signal. We denote the event-induced traits as event descriptors. Here we see the desired clusters where the clips are grouped by their devices or domains rather than events. That means we want to cluster them using domain characteristics which we define as domain descriptors. But they are usually subtle and often get masked by event descriptors. So we need an algorithm to remove event descriptor from signal and cluster them based on domain descriptor. To this end, I propose a multitask neural network for domain-wise clustering that has 2 primary tasks: to extract event-agnostic signal representation and to cluster signals based on domains. First, I will describe the event-agnostic representation part. Here we have an encoder-decoder to extract feature from the input signal. The encoder network, which is a convolutional neural network, compresses the input into a low-dimensional vector that contains necessary information so that the decoder can reconstruct the input from this vector. The decoder has the same network structure as the encoder, but with transposed convolutions instead of standard convolutional layer. We use mean squared error as loss function that minimizes the square distance between the input signal and the output from the decoder. This encoder-decoder branch maintains the structural integrity of the signal. The encoder compresses the signal into the low-dimensional feature and it contains both event and domain descriptors. To remove the event descriptors from the feature, I propose to use another branch of fully connected neural network to predict the class levels. As we have class levels available in the training dataset, we can use them to train this branch using cross-entropy loss. However, this branch extracts the feature dominant for audio events, which is opposite of what we desire in our case. To remove that extracted feature, I propose to use a gradient reversal layer in between the fully connected layer and the output of the encoder. During backpropagation, it multiplies the gradient from its following layer with a negative scalar value of lambda and then passes it to the preceding layer. During the forward pass, this layer acts as an identity transformation so that it does not have any effect on the inference process. Backpropagation of the gradients through the network forces the weight updates that minimizes the loss function. In a general scenario, the network would update its weights such that the event descriptors are dominant in the feature representation, and it achieves a higher accuracy in the audio event classification task. Inserting a gradient reversal layer in between the fully connected network and the feature from the autoencoder reverses the gradient during backpropagation. As a result, we are able to form a minimax situation where the fully connected layers try to reduce the loss function while the gradient reversal layer makes sure that the preceding layers do not succumb to this. Hence, in effect, the fully connected layers are extracting the event descriptors from the feature representation while the gradient reversal layer is removing them. With the removal of event descriptors, we obtain an audio representation that contains primarily the domain descriptors. We perform clustering on these representations to get the desired domain-wise clusters of the input signal. We use a deep embedding clustering branch to perform the clustering. The deep embedding clustering branch clusters data in unsupervised manner by updating the cluster assignment using soft assignment. It further updates the feature space and cluster centroid using self-training by learning from high probability assignment. The next step is domain adaptive classification. After finding the domain levels, we use them to remove biases from the classifier. The goal of domain adaptation layer is to reverse the effect of domain shift. Inside a neural network, the effect of domain shift is observed at the activations of each layer. Input data from different domains cause different amounts of shifts in the activation of the same layer of the neural network. In the figure, we see the distribution of activations of same layer for 2 different domains have different distributions. In order to normalize these shifts, for each input domain, we collect the running mean and variance of the activations. These statistics are used to shift and scale the activations to match with the reference distribution having a zero mean and unit standard deviation. Here we see the equation for the task for a domain DI and a hidden layers activation. Here mu and sigma are the running average and variance of the activation output. The domain adaptation layer can be used to retrofit popular neural network architecture for audio classification tasks such as VGG, inception, and so on. Here we can see the domain adaptation layers are inserted after the traditional neural network layers such as convolutional layer and fully connected layer. To evaluate our proposed system, we construct a multi-domain dataset. We record audio clips using 5 types of microphones interfaced with Raspberry Pi, a laptop, and a desktop machine to further introduce system-induced variability in the data. We play all sound clips from the ESC10 dataset on an omnidirectional speaker by keeping all 5 microphones equidistant from the speaker. ESC10 is a popular dataset used for sound event recognition that contains environmental sounds. The microphones are synchronized to record the audio simultaneously. We also collect a dataset containing audio clips with the same device from different environments. We use this dataset to evaluate the ability of our system to discover and adapt domain shifts due to environmental heterogeneity. We also use a public dataset given in the case 2018 challenge that has synchronous recordings from 3 different microphones. The dataset contains recording of 10 different types of acoustic events such as train station, public square, streets, etc. Here we see the statistics and the type of events that are present in these 2 datasets. Now we report the performance of our proposed unsupervised domain discovery by varying the number of domains. We compare our proposed algorithm with the current state of the art. We observe that sound adapter shows the best performance among all approaches. For 2 domains, sound adapter achieves an accuracy of 96%, whereas state of the art have maximum 77% accuracy. As the number of domains increases, sound adapter outperforms the baselines by larger margins. For 3 domains, sound adapter discover domains with 91% accuracy, whereas the state of the arts have a maximum accuracy of 56%. As the number of domains increases, sound adapter's performance drops to 76% for 5 domains, which is still more than 30% higher than the best of the 3 baselines performance. Now we present the performance of domain adaptation. We report the loss of accuracy of sound adapter, which is the end-to-end pipeline and an oracle system that is using only our domain adaptation technique but with ground truth domain levels. We also report 2 baseline algorithms, mic-to-mic and standard convolutional neural networks performance. All of the numbers are calculated with respect to the same source, same target scenario. A lower accuracy drops indicates a better domain adaptation capability. We observe that the oracle has an accuracy drop of 3.7 and 1.3% for the empirical and the decades dataset. For sound adapter, we observe a drop of 6.7 and 4.1% for these datasets. On the other hand, the state of the art has 15 and 12% accuracy drop. Therefore, it is evident that from the performance of sound adapter and oracle, our proposed domain adaptation algorithm is able to recover accuracy loss for multi-domain adaptation. So in summary, in this paper, we study the problem of multi-source domain adaptation for audio data. We propose an unsupervised clustering algorithm for domain discovery for audio data. We propose a domain adaptation layer to remove domain bias from machine learning classifier. Further, we collect empirical dataset using multiple devices and evaluate our proposed algorithm using both collected and public dataset. Thank you.